Hello James, welcome back to another video. In this video, we'll be discussing the frequently asked BITSAT questions from the chapter of gravitation. And without even wasting a second more, let's begin. So before we dive directly into lots and lots of questions, let's briefly discuss the topic weightage for this chapter. Now this topic weightage is as per the last 15-year BITSAT trends. Okay, so let's see which topic is more important as far as BITSAT is concerned. Okay, before that, gravitation in itself is a very important chapter for BITSAT, and you will at least find 4 to 5 questions from this topic in the paper that you are going to answer. Okay, yes. And now let's see which topic is more favored in BITSAT. So coming to our first topic, which is universal law of gravitation, only one question was asked from this topic over the last 15 years, and this question was pretty much formula based. You just had to use F equals gmm by r square. Okay. Next topic, we have variation in acceleration due to gravity, small g. Okay, now you'll see the weightage is almost uniform over the other topics. Okay, so yes, from this topic, mostly the questions were asked based on the dependence of your acceleration due to gravity on angular speed. Okay, so 2 out of these 3 questions were based on the dependence on angular speed, and this one was based on your height and depth. Okay. Now the next topic that we have is gravitational field and potential. From this, we were asked 3 questions, and most of those questions were based on gravitational field or potential due to your spheres. Okay, maybe due to a solid sphere or a spherical shell. Okay, so from the potential and field region, more focus was given on spheres, shells or solid spheres. Okay. Next topic that we have is gravitational potential energy. Again, 3 questions from it, and this were pretty conceptual. Okay, you had to use the concept of potential energy. Of course, you'll find potential energy can be easily composited. It can be mixed up very well with the other topics as well. So yes, it's a conceptual thing. Okay, and also you'll know the formula. It's gmm by r. So sometimes they might ask you to find the potential energy of a configuration. Okay, again, concept is the thing that you should know well in such cases. Again, we'll come to problem, don't worry. The next topic that we have is escape and orbital velocity, one of the most favorite topics from this chapter of your BITSAT. So 5 questions were asked, and recent questions are also asked on escape velocity. So this is something that you should focus on. So yes, questions on escape velocity and orbital velocity, sometimes formula based, straightforward. Okay, and sometimes a bit conceptual. Okay, and then we have questions being asked on satellite. From satellite, again 3 questions. So questions based on the orbital velocity of satellite maybe, or the total energy of a satellite in a particular orbit, or the energy required to move a satellite from this orbit to that orbit. So that kind of questions. Okay, and then finally we have Kepler's law. From this we were asked questions. 2 questions were asked from this topic, and they basically had to do with the third law, Kepler's third law, which says that the time period in a particular orbit is the square of the time period is proportional to the radius cube, right? So yes, this was the topic weightage for BITSAT over the last 15 years, and let's do some questions now. So let us begin our discussion today with the topic variation in acceleration due to gravity. Okay, I know the first topic that I mentioned was universal law of gravitation, but the questions there are pretty straightforward and formula based, so it will be just a waste of time to discuss those type of questions. Okay, so let's directly start with variation in acceleration due to gravity. So question number 1, average density of Earth is. Okay, so you basically have to find a relationship between average density and acceleration due to gravity, and see how does your acceleration due to gravity depend on average density. Okay, so that is what the question is saying, although it's framed in a bit absurd manner. You can see average density of course does not depend on acceleration due to gravity, but of course acceleration due to gravity depends on density, right? So anyway, so just find a relation between these two. So first of all, you can write the acceleration due to gravity as gm by r square, right? Acceleration due to gravity can be written this way. Okay, I hope you know this formula. We are going to see this a lot of times in our discussion today. Okay, now I can write this mass as density into volume, right? Basically my idea is to find a relationship between these two, right? So G can be written as G, capital G, which is a constant. A mass can be written as density into volume, and treating Earth as a sphere, we can write it as 4 by 3 into pi r cube, right? Density into volume. Just we are treating Earth as a sphere, although it's not approximating. Okay, so here we'll have r square will cancel with this. So finally we have G rho, okay, I'll write it in a proper manner, 4 by 3 pi G, then again we have R, and finally we have rho. So you can see all the quantities that I've put in this braces are constants, right? So 4 by 3 constant, pi constant, G is the universal gravitational constant, R is radius of Earth constant, and finally we have density. So you can see the direct relation between the two, right? So your acceleration due to gravity directly depends on density. Yes, pretty obvious. More dense means more acceleration due to gravity. Okay, so something which is more massive and smaller than Earth will have a higher acceleration due to gravity. Okay, because more density means higher acceleration due to gravity. Okay, so yes, option D, directly proportional to acceleration due to gravity. Okay, although gravity acceleration due to gravity is directly proportional to average density. That is the way the question should have been framed. Okay, now coming to question number 2. Okay, so you are supposed to tell a height where acceleration due to gravity becomes 1/9 of its initial value. Okay, so this is the acceleration due to gravity on the surface of Earth. Okay, it will become 1/9 of its value at what height? Okay, or at what height will the acceleration due to gravity will become 1/9 of its value at the surface? Okay, now you might be tempted to use this formula that G dash is G into 1 minus 2h by r, right? This is how your acceleration due to gravity depends on height. Okay, this is how it varies with height. Okay, but keep in mind that this formula is only valid if h is pretty much smaller than r. Okay, this formula is only valid under this condition. If you see h over here, the options you can see, okay, these are the values of h. Okay, one of this is true, of course, but you can see that this h is pretty much comparable to r. Okay, it's r by root 2, r by 2, root 2r, or 2r. Okay, it's comparable to r, so you cannot use this formula. Okay, this formula is only applicable in this condition. Okay, so what to do now? So you just have to look over here. You can easily see that G is inversely proportional to 1 by r square, right? R being the distance over here. Okay, not necessarily the radius, r being the distance. I'll use small r over here. Okay, so yes, G is inversely proportional to r square, right? So here G is constant, and m, mass of Earth, is also constant, so it's inversely proportional to the distance from the center, right? So that is what I'm saying. So from this we can write, we can take the ratio of G dash by G. Okay, G dash by G. So this will be inversely proportional to the height. So I'm saying the height in this case is r plus h. Okay, and whole square. Okay, I hope you are getting this. So we have moved a distance h from the Earth's surface. H is of course measured from the surface, and r should be the distance from the center, right? So it is r plus h. Here the acceleration due to gravity is G dash. Okay, so G dash is inversely proportional to r square. What is r square over here? R plus h. Getting? Yes. Okay, so yes, once you get that, it's very simple. And G is the acceleration due to gravity at the surface. At the surface, it's basically r square, right? The distance from the center is r square, the radius square. Okay, distance is r, it's square. Okay, and then we can substitute now G dash. We want it as G by 9. So G by 9 upon G, G and G will get cancelled. So r square, and here we'll have r plus h, or I can simply write this as r upon r plus h, the whole square. So we have G and G by 9. Okay, G by 9 and G, the G cancels, and this is whole square. Just solve it, take root on both the sides. It's 1 by 3 r. Here you'll have r plus h. So r plus h is 3 times of r, or h is equal to 2r. So this is nothing but your answer, right? So the height is 2r. So at a height of 2r, okay, at a height of 2r from the surface of the earth, of course height is measured from the surface, so yes, at a height of 2r, the acceleration due to gravity will become 1/9 of its initial value. Okay, yeah, so that is the solution. Let's move to some more questions from this topic now. So question 3 and 4 over here, of course on the same topic, but these questions have to do more with the dependence of your acceleration due to gravity on the angular velocity. Okay, so let's see them. So question number 3, in this question you are told that when the earth is not rotating, of course it's hypothetically created, okay. So this scenario, suppose the angular velocity of the earth is 0, it's not rotating. In that case, the weight of an object placed at the equator will be w, okay. So you are asked what should be the angular velocity of the earth so that the weight becomes 3/4 of the original weight at equator, okay. So basically you can see that weight is given as mg, right? Weight is mg. A mass of the object of course remains constant. Weight is directly proportional to acceleration due to gravity, okay. So in this case where the weight is becoming 3/4, actually the acceleration due to gravity is becoming 3/4. That is why the weight is becoming 3/4, okay. So just picture it. Since the earth is rotating in the second scenario, the acceleration due to gravity, the effective gravity is decreasing, okay, and due to that the acceleration due to gravity is becoming 3/4, and due to this the weight is becoming 3/4 because they are directly related, okay. So let's see now. So effective gravity should become 3/4 of the initial gravity, the gravity in this case, okay. So that is our thought process over here. So we can use the relation g dash equals g minus r omega square cos square phi, right? So I hope you know this relation. This shows the dependence of your gravity, acceleration due to gravity on the angular speed omega. Okay, so omega is the angular speed, r is the radius, cos phi, I'll tell you about phi when we actually imagine that, okay. So now g dash, it should become 3/4 for the weight to become 3/4. So g dash is 3g by 4, okay. Original gravity is g, it's the value is given but we'll substitute it later, okay. Then we have r omega square, again r is given, we'll substitute it later. Omega square we are supposed to find, okay. What is the omega when gravity becomes 3/4 or the weight becomes 3/4? So you can see the question over here as well, okay. So now what about phi? Now phi is basically, you can imagine this in 2D, okay. This is earth, suppose this is the center of the earth, and you can imagine this diameter, okay. So phi is basically the angle. Suppose our particle is placed over here, okay. In this case of course it's placed at equator, but let's take a general case where the particle is placed somewhere over here on earth, okay. So phi is nothing but the angle over here, okay, between the horizontal line and the line joining the center and the particle. It's the angle between the horizontal line, okay, and the line that is joining the center and the particle, okay. So of course in our case the particle, now this is phi, right? So in our case the particle is at the equator, it's of course on that horizontal line itself, okay. So what will be phi? Phi will be 0, right? Because our line will be along the horizontal line, or in that case the two lines will merge and phi is 0, okay. So in our case equator, phi is 0, okay. So cos of 0 is 1, okay. So just it's 1 square, so no need of writing that. Now solve this. R omega square will be given as, so g minus 3g by 4, okay. Just switching it, g minus 3g by 4, so 1 minus 3/4, that is 1/4, so g by 4, and omega square will, so omega we have to find, so omega square is g by 4, so 10 by 4 is 2.5, 2.5 divided by r is 6400, so 6400 kilometers, okay. You have to convert that in meters, so 6400 into 10 to the power 3, okay. Now 25, so 2.5 I can write it as 25 into 10 to the power minus 1, so shift the decimal to the right hand side and into 10 to the power minus 1, okay. And that again this 5 zeros we have, right? So in the denominator we have 10 to the power minus 5, and that will go on top, 10 to the power 5, that will go on top as 10 to the power minus 5, and again with this one it will become 10 to the power minus 6. Okay, so just do the maths, only maths is remaining. Physics is done, so yes, 25 by 64. Now this is omega square, so omega have to take root on both the sides, so 5 by 8, okay, into 10 to the power minus 3, right? So 5 by 8, 5 by 10 would have been 0.5, half, right? But 5 by 8, so it's greater than 0.5, okay, since the denominator is more, it's less, so it's greater than 0.5, so greater than 0.5, and it will be, I guess, 0.63. Okay, you can check it, I'm not pretty sure, but I think that would be the answer, 0.63. Okay, please check it. Now coming to our next question, again it's based on the very same concept. So if omega increases, then you are supposed to tell what will happen to a weight of an object. Okay, okay, so will it increase everywhere, decrease everywhere? So that way you have to tell. Okay, you can easily see by this relation, g dash equals g minus r omega square cos square phi. Okay, so if omega increases over here, right, if omega increases, this term will increase, right? If omega increases, this term will increase, so g minus a bigger term. So the effective gravity is decreasing, effective gravity is decreasing, effective weight is decreasing. So weight will decrease, right? And it should decrease everywhere. So I think option B should be correct. Actually, no. Okay, so the weight will of course decrease, but not at the poles. What is happening at the poles? You can see over here. Okay, so you can imagine at the poles we have this, right? Pole is either north pole or south pole. Okay, so at the pole, suppose we have a particle at the pole, the angle over here becomes 90. With the horizontal line, the angle becomes 90. So phi over here, in the case of poles, it's 90. In case of equator, it was 0. In case of poles, it is 90. So cos of 90, 0. This term itself becomes 0. Okay. So if you place an object at the pole, okay, yeah, it would not depend upon omega. Okay, is it making sense? Because if you see the rotational axis is this and the point lies on the rotational axis, or you can see it by the relation cos of 90 is 0. Okay, so this entire term will become 0, g dash will be g only at pole, right? So at the pole, the angular velocity does not affect your acceleration due to gravity. Okay, so your weight will decrease at all other places except the poles, because at the poles this term becomes 0. Otherwise this term is not 0. On increasing omega, the term becomes bigger and your effective gravity lessens. Okay, that is what is told. Weight decreases but not at poles. Okay, weight decreases everywhere except the poles. That is the correct answer over here. Okay, so let's move to our next topic now. Now the next topic that we are discussing is gravitational field, gravitational potential and potential energy. Okay, so let's start with it. So in question 1 we have a shell and a solid sphere. The solid sphere has a mass m, capital M, and a radius a. Okay, shell is also concentric to it. Okay, and it has a mass 2m. Okay, shell has mass 2m and radius 2a. Okay, now we have a mass m at a distance 3a from the center of this two concentric shell and solid sphere. Okay, so from the center this distance is 3a. You are supposed to tell what is the field on m, what is the gravitational field at m or on m. Okay, now it's very simple. If you see the gravitational field at m or on m will be basically due to this solid sphere and will be due to this spherical shell, right? And if you see, it is a point which is outside both the spheres. Okay, it's outside the solid sphere and it's also outside the shell. Okay, and for points outside, the gravitational field is basically given as gm by r square. Okay, gm by r square, where r is the distance from the center. Okay, now let's find it out. Okay, so the field on m will be due to the solid sphere. So basically the net field on m will be due to the solid sphere. Okay, and plus the field due to the shell. Okay, both the fields will be in the same direction towards the center, you can see, right? So you can just add, okay, although it's a vector, they are both will be in the same direction, okay? So you don't have to worry about the angle between them and this and that. You can just add it because they are along the center, towards the center, in the same direction, okay? So the electric field due to the solid sphere is gm, mass of the solid sphere, capital M, divided by r square, where is what is the distance? 3a square, right? Distance of small m, okay, from the center. So 3a, it is the distance, so 3a square, which is 9a square, okay, plus g m by r square. Again, for the spherical shell, the point is outside, so again g m by r square. So g, the mass of the spherical shell, the mass of the shell is 2m, okay? So g into 2m, so I can write it as 2gm, upon, again, the distance from the center is 3a square, yes, 3a the whole square, that is 9a square, okay? So you can add this, gm by 9a square plus 2gm by 9a square, that will be 3gm by 9a square, or you can simplify it as gm by 3a square, gm by 3a square. Option A is the correct choice over here, okay? Now let's come to question number 2. Here you have two solid spheres and the graph of their gravitational potential against the distance is plotted over here, okay? Sphere 1 has radius 1 meter, sphere 2 has radius 2 meters. You are supposed to find the ratio of their masses, okay? Find the ratio of m1 by m2, okay? Again, we can use the same logic, okay? We'll use the gravitational field. You can see different values of gravitational field. You are sure about these values, right? So here the point is being marked for you and we can use it. 1 is the radius of first solid sphere and 2 is the radius of the second solid sphere, right? And what is the gravitational field at the surface? At the surface, the gravitational field is basically gm by r square, okay, where r is the radius this time, okay? So here it's gm by r square is the distance from the center, and for a point on the surface it's basically gm by r square. It's pretty much analogous to your electric field concept, okay? So this is like gravitational field at the surface, okay? So for sphere 1, solid sphere 1, we can write E1 will be equal to G is a universal gravitational constant, M1, mass of your first solid sphere, divided by R1 square. R1, radius of the first one is 1, so 1 square, that is, I'll write that, 1 square, that is again 1, okay? So Gm. So E1 is basically Gm1. So Gm1, if you see the value at the surface of the solid sphere 1, okay, so value at the surface, okay, is 2, okay, whatever that unit is, so 2 value at the surface. You can see that this is for 1, okay, I forgot to mention that this is for sphere 1, this is for sphere 2, okay? So for sphere 1, the value of the electric field when when the radius is 1, okay, yes, of course the radius is 1, so the value of the electric field in that case is given as 2, okay? So yes, so E1 is 2 over here, okay? And E2, similarly you can write gm2 by r2 square, r2 2 square, which is 4, okay? E2, if you see electric field at the surface of second sphere, right? Electric field at the surface of second sphere has radius 2, so surface will be at 2, okay? So 2, so if you see field at 2 is 3, okay? So I'll directly write 3 over here, and gm2 will be nothing but 3 4s are 12, okay? So gm1, gm2 you can divide both, so you'll get m1 by m2, g will cancel, will be 2 by 12 or 1 by 6, okay? So option B, 1 by 6 is the correct choice over here, okay? So you just have to use the formula gm by r square. R is the because it's on the surface, r is the radius, okay? So for both spheres, and you directly have the value at the surface. For sphere 1 it is 2, for sphere 2 it is 3, okay? So E1 is 2 and E2 is 3, okay? So you just have to look at the graph, watch it properly and solve this equations using that, and yeah, that gives you your answer. Okay, so let's move to the next question now. Question number 3 over here, again from the same topic of gravitational field, potential and potential energy. Okay, so in this question we have two masses m and 4m which are separated by a distance r. We are told that at this point P, it is a point between these two masses along the line joining them. It is such a point where the gravitational field becomes zero. Okay, you are supposed to tell what is the gravitational potential at that point, okay, at that particular point, which is P in our case. Okay, so again, I'll repeat the question. We have two masses separated by a distance r. We have a point P along a line joining the two masses, okay, such that at this point P, the gravitational field becomes zero. Okay, you are supposed to tell what is the gravitational gravitational potential at this point. Okay, so there is a typical approach to solve this question. Okay, so first of all, we'll assume that the distance of the smaller mass, okay, from this point P is x, okay, and here what will be this distance? This distance will be r minus x. Okay, so this distance is x, so this will be r minus x, right? This, right? So now, of course, you can assume it vice versa also, this r minus x and that x. Okay, nothing's wrong with the assumption. Okay, so yes, now we have to find this value of x in terms of r. Okay, so we have to locate where is this point x. Okay, we want to find the value of x in terms of r. Okay, so we'll use this data now. We are given that the electric field at that point is 0. At point P, the electric field is 0. Of course, you can see that the mass, okay, this mass, the electric field will be in this direction, the gravitational field will be in this direction, and here the gravitational field due to this mass will be in this direction. So at point P, it is such a point that these two magnitudes are equal. Magnitude wise, the field due to 4m and due to m are equal at this point P, but they are opposite in direction. That's why the gravitational field is becoming 0. Okay, so the magnetic field, what am I saying? Oh my god. The gravitational field due to m is equal to the gravitational field due to 4m. Okay, this is happening because first of all, your electrostatics, your electric field and the gravitational field have basically the same concepts, and today we just learned in our college about magnetic fields. Okay, so that is why I'm mixing all of it up. Okay, so magnitude wise, magnetic, okay, sorry. Okay, the gravitational field due to mass m is same as the gravitational field due to mass 4m. Okay, magnitude wise. So how is the field given? I'll just say field now. Okay, so the field is given as for a point mass, it's basically gm by r square, right? Gm, so g, the mass of that particular source. Okay, here the source is m, here the source is 4m, and here divided by the distance from that point. Okay, so due to the mass m over here, what will be the field at P? So it will be g m, right, this mass divided by the distance from point P, which is x square. This is the field at point P due to mass m. Now what will be the field at point P due to mass 4m? So it will be g times 4m, this mass, so 4m divided by this distance, which is r minus x square, r minus x the whole square. Okay, g and g will get cancel, m and m will also get cancelled. R minus x square, r minus x the whole square is equal to 4x square. Okay, now we can actually take roots on both the sides. Okay, so it will be r minus x is equal to I'm only considering the positive value because the negative value will give us point P over here. Okay, we want the point P between these 2 points. Okay, so yes, also you can expand this and then make it a quadratic and then solve for x. Okay, so in that case also you'll get two values. You have to discard the negative value. The negative value basically will be a value on this side. Okay, but we want point P between the two masses, right? Fine. So yes, I'm just discarding the negative value. Okay, so I'll get this thing. right? I took root on both the sides, yes. So it will become r is equal to 3x, or x is nothing but r by 3. Okay, x is nothing but r by 3. So our first purpose is done. We have located the point P. Okay, we know the position of point P now, where the field becomes 0. It is r by 3, 1/3 of the total distance. Okay, so x is r by 3, and it's closer to the smaller mass m. Okay, do you know why? Do let me know in the comment section. Why is this x value, or why is this point P closer to the smaller mass? Why not to the bigger mass? Okay, answers in the comment section. Okay, now let's proceed. We are supposed to find the gravitational potential at this point P now. Okay, so let's find out. Now the gravitational potential is a scalar. It does not have direction, right? So you just have to find the gravitational potential due to this mass, the gravitational potential due to this mass, and then just add. Okay, how is the gravitational potential given? I'll use a letter V for it. So gm by r. Okay, so 1 less r. Okay, so gm by r. That is how the gravitational potential is given for a point mass. Now let's do it. So due to the smaller mass, we have gm by smaller, right? Due to the bigger mass, which is 4m, we have 4gm. Sorry, what is that distance? The distance over here is gm by, at point P, right? So gm by r by 3. Okay, x is r by 3. So gm by r by 3. So that will become 3gm. And here we have gm is 4m over here. And the distance is the distance of 4m from point P, which is 2r by 3. Okay, r minus x, you can calculate that. So r minus r by 3, that is 2r by 3. Okay, so this distance is 2r by 3. So this and this can get cancelled. This will give you 2 3s are 6. So 6 gm by r, and this is 6 plus. So you just have to add this 2. Potential is a scalar. You can directly add it. So V net will be 3 plus 6, which is 9 gm by r. Yes. Okay, and of course a negative sign, because here the potential basically is minus gm by r. Okay, so this both will be negative, because the force just you have to show the attractive nature of the force. Okay, so yes, it's negative, don't worry about the sign. So the correct answer over here is minus 9 gm by r. Okay, so minus 9 gm by r is the correct choice over here. Okay, so first we equated the electric field due to this mass and this mass at point P. Okay, that was given in the question. The field is 0 because the field due to this mass and this mass are cancelling out. They are equal in magnitude. Okay, we assign this distance x. This will be r minus x. Then use this formula, substituted, found the value of x, found x in terms of r. Okay, so we could locate the point P where the field is 0. Okay, and then we solved for this. Okay, so we found the potential due to mass m at point P, the potential due to mass 4m at point P. Okay, and then potential is a scalar. Just add the two numbers. Okay, two values. So that is how you do question number 3. Let's move to the next topic now. We'll do the questions on potential energy more when we come to satellite. Okay, so it's basically very simple. So our next topic is escape and orbital velocity. So question 1, what is the kinetic energy that is required to project a body so that it escapes to infinity? Okay, now well, you might ask, how is this related to your escape and orbital velocity? Actually, this question is in a sense the true concept of your escape velocity. Okay, the concept of escape velocity says that the final total energy of the object which is projected should become 0 for it to escape to infinity. Okay, should at least become 0 for it to escape to infinity. Okay, so basically when the total final energy becomes 0, your object was given escape velocity. That is reverse engineering. Okay, so yes, so this is the true concept of escape velocity. Okay, final total energy becomes 0. Now you can use the conservation of energy. So kinetic energy initial plus potential energy initial equals or I can say kinetic energy final plus potential energy final, or that can be treated as total energy final. We know that the object is escaping to infinity, so the total energy final is 0. Okay, now we are supposed to find what is the kinetic energy that we gave, the potential energy. Okay, so we'll consider the object is on the surface of earth, so potential energy in that case is nothing but minus g small m capital M by r, right? R will be nothing but the radius of the earth, right? So it's distance from the center, which is capital R, or this will be 0. Kinetic energy will be g m by r. Okay, so this is the energy that we need. Now we can in fact write gm as gr square. This is the relation that I told you in question 1 that we discussed today. Okay, not this question 1, the question 1 from topic 1. Okay, so gm is equal to gr square. Now is the time to use it. So gm, we can replace it by gr square, and here we also have a m, so that m, and here this will cancel, and finally our answer will be mgr. Okay, so option C, mgr, is the correct choice over here. Okay, so this amount of kinetic energy should be given for your object to make it escape to infinity. Okay, and this, please remember, is the true concept behind your escape velocity. This is the idea behind escape velocity. Okay, now coming to our second question, the escape velocity from the surface of the earth is given as 11 kilometers per second. Now your object is projected at an angle of 45 degrees. You are supposed to tell what will be the escape velocity in this case. Okay, so if you want to project your body at 45 degrees, will the escape velocity be any different? Okay, if yes, what will be it? Okay, actually the escape velocity, it's quite obvious, would not be any different, right? Because it's just a matter of total energy becoming 0. So if you give enough kinetic energy, it's a matter of energies, right? Energy is a scalar, so direction will not matter. Okay, so if you see velocity, it's a vector, so in a way direction should matter, but the true concept behind escape velocity is energies. Okay, it's the total final energy becoming 0. Its energy is a scalar. So even if you change the angle, even if you change the direction, if you project a particular thing with the escape velocity, the escape velocity basically does not will not depend on direction or angle, right? So even if I project this horizontally with escape velocity, which is 11 kilometers per second, it will escape the gravitational field of earth, provided nothing comes in the direction of it. Okay, so again, the escape velocity does not depend on your direction or angle, so it will remain same. Okay, because it's a matter of energy. And let's move to the next questions now. So question 3 and 4 over here. In question 3, we are told that we have a planet, okay, so which is 10 times heavier than Earth. So mass of that planet is 10 times the mass of the Earth. Also the radius of that planet is given to be 1/10 of the radius of Earth. Okay, and it is told that the escape velocity on Earth from the surface is given as 11 kilometers per second. You are supposed to tell what will be the escape velocity from the surface of that planet. Okay, now it's quite evident if you see that planet is more massive and it has a smaller radius. Okay, so it's more dense in a way. Okay, so you can also see that since it's more dense, the acceleration due to gravity there will be more, right? Question 1 of today, gravitational, the acceleration due to gravity is directly proportional to density, right? So in that scenario, our escape velocity should of course be greater than 11, because the planet that we are discussing is more massive and smaller in radius with respect to our Earth, right? So our escape velocity should be greater than 11. So this is not the correct choice. This is also not the correct choice. So either option B or C. Okay, this was a way of manipulating and eliminating the options that are not logical over here. Okay, but now let's try to solve it. Okay, so we can write the escape velocity of Earth as a formula g, which it will be 2gm E by RE. Okay, I know you might remember it in terms of acceleration due to gravity. That is easier to remember, but this is a better version of the formula, I would say. Okay, so please remember this formula too. Okay, so escape velocity of Earth is given in this way, and we are told that it's 11 kilometers per second. Now escape velocity of this planet will be similarly 2 gm. Now mass of this planet divided by radius of this planet. Okay, now let's substitute it in this way. So 2g, mass of that planet is 10 times the mass of Earth, and the radius of that planet is 1/10. So re by 10, that 10 will go on top, and that 10 and this 10 will become 100. Okay, so if you see 10 10 100, or I can get it out of the root sign, and what will we be left with? 2gme upon re, right? 10 10 out of the root sign, so 2gme by re, which is nothing but the escape velocity of Earth, right? And which is nothing but 11. So 10 times 11, which is 110. So 110 kilometers per second is the correct choice over here. Okay, I hope the approach is pretty simple. I hope you know this formula, that escape velocity is given as under root 2 gm upon r. Okay, now let's come to question number 4. We have a satellite which is at a height h, which is way more smaller than the radius. Okay, so you can just consider the satellite as very close to the surface. Okay, and then you are supposed to tell what is the minimum velocity. Okay, so what should be the minimum increase in the velocity so that your satellite escapes to infinity, or the satellite escapes the gravitational field of Earth. Okay, now it's pretty simple. You can see that h is pretty much smaller than r, so you can use the relations of escape velocity as under root 2 gr. Okay, this is a relation when your object, the body, is given the velocity from the surface. Okay, so this is a relation. This is the escape velocity from the surface of Earth, because since this distance h is pretty much smaller than r. Okay, it's way much smaller than r, so we can consider that this satellite is very close to the surface, right? So we can use the same relation. That is what I'm saying. And also the orbital velocity will be under root gr. Okay, now you want to find the minimum velocity so that your uh, satellite escapes, right? So basically you have to find the difference between these two, right? This is the velocity change, or this is the increase in the velocity that you want so that your satellite escapes, right? This is the velocity with which the satellite is orbiting in the orbit, right? And this is the velocity which, when given, your body or satellite will escape the Earth's gravitational field, right? So the difference between the two is nothing but the minimum velocity that should be given so that your satellite escapes. Okay, so this minimum velocity will be under root 2 gr minus under root gr. You can take under root gr common. It will be under root 2 minus 1. Okay, root 2 minus 1. Yes, option B is the correct choice over here. It's quite simple. Let's move to the next question now. Our topic number 4, which is satellite. Okay, so in this topic you are told that what should be the minimum energy to launch a satellite which is on the surface of Earth to orbit of height 2r. Okay, so you want to launch a satellite from the surface to this orbit which has a height 2r. Okay, so this will be 2r. Remember that the height is measured from the surface, right? So this is 2r, not the distance from the center. Okay, so the distance from the surface to the orbit is 2r. Okay, so the total distance from the center will be 3r. R plus 2r, that will be 3r. Okay, so that was a point to consider. Now we have to find minimum energy. Okay, so first of all, the thing that I'm thinking about is to conserve energy. Okay, so I'll use kinetic energy, initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy, or I can directly write it as final total energy. Okay, now we are supposed to find this. What is the minimum kinetic energy, okay, more specifically, to launch this satellite into the orbit. Okay, so because initial potential energy is something which we directly know, right? Initial potential energy will be nothing but, since the satellite is on the surface of Earth, it will be gmm by r, right? This is the potential energy on the surface of Earth. Okay, so now, what about the initial kinetic energy? That is something which we want to find, right? That is the minimum energy we are talking about. What about the total final energy? Actually, you can find the kinetic energy, final potential energy, then add the two. But a final total final energy will be simply given as, I hope you know this formula. It is minus gmm by 2r. Okay, where r is the distance from the center. Okay, minus gmm by 2r. The final kinetic energy, okay, is nothing but, you'll know about this. Okay, so it's same as the total energy, but it is positive. Okay, they basically differ in sign. Okay, and what about the final potential energy? Okay, so these are the three relations that you should know about. Final potential energy, gmm by r. Okay, so yes, where r, everywhere over here, the r stands for distance from the center. Okay, and the other letters have their usual meaning. Okay, so you can see that total energy is minus gmm by 2r. Okay, so let's substitute it over here. So initial kinetic energy, we'll find that final initial potential energy minus g capital M small m into r. Now this r is on the surface, right? This is initial potential energy. The satellite initially is on the surface of Earth, so that r is nothing but the radius of Earth. Now total final energy is this, is minus gmm by 2r. Now r is the distance from the center. R is the distance from the center. Now finally the satellite will be over here, right? So yes, so finally the distance is 3r. Distance from the center is 3r, not 2r. Okay, because this is height. Height is measured from surface. Distance is measured, this distance r is measured from center. Okay, so kinetic energy, you can write it as minus gmm by 6r, and this will go on the other side as plus gmm by r. Okay, so 1 minus 1/6, that is 5/6. So 5/6 gmm by r. Okay, so option A, 5 by 6 gmm by r, is the correct choice over here. Okay, so these are few relations that you should remember. You can also remember that total and the kinetic energy only differ in sign. Potential energy is 2 times of the total energy. Okay, potential energy is 2 times of the, when you multiply 2 and 2 will get cancelled and you'll get this. Okay, so potential energy is 2 times of total energy, and kinetic energy and total energy are same magnitude wise but differ in sign. Okay, so yes, this is the initial energy, the minimum energy that we should provide so that our satellite reaches this particular orbit. Okay, now let's move to our last topic, which is Kepler's laws. So question 1 and 2 from Kepler's law. Question 2 is a homework for you. It's a question based on this Kepler's second law, okay, and the fact that aerial velocity is constant. Anyways, let's come to question 1. So in this question, you are told that when the radius of orbit is r, time taken is 5 hours for the satellite to revolve around that orbit. Now what will be the time taken if the radius of the orbit becomes 4r? Okay, now it's quite simple. You will know Kepler's third law directly, that the time period along the orbit is directly proportional, the square of the time period is directly proportional to the radius cube. Okay, so you are just simply supposed to use this. So t dash by t the whole square, okay, will be equal to directly proportional to the radius cube. So r and r dash I'll use. So r dash, so corresponding to this we have r dash, corresponding to t we have r. Okay, this cube. Okay, so t dash square will be given as r dash cube. So r dash is 4r, and divided by r is capital R, and this cube into t square. Okay, this t I'm taking to the other side, t square. So 5 square, that is 25. Okay, again this and this will get cancelled. T dash square is 4 cube is 64 and into 25. Now you can take root on both the sides, so this will become t dash. 64 root is 8, 25 root is 5, so 5 8s are 40. Now this was in hours, so this will be also in hours. So option C, 40 hours is the correct choice over here. Okay, now this question is your homework question. As I said, it's based on the concept that aerial velocities are constants. Okay, so here basically you are told that the time taken to travel this distance POA by a satellite is T1. Okay, and the time taken to travel this distance from OBP, this time is T2. You are supposed to find the relationship between T1 and T2. Okay, it is also given that the area of SOP, this triangle over here, is 1/4 of the area of ellipse. Okay, so do give this question a try. Do let me know the answers in the comment section. If you give me the correct answer, I'll give you a heart. And make sure you like this video if you enjoyed it. And consider subscribing. More BITSAT content is coming up for you. I'll see you soon in the next video. Till then, keep enjoying physics.